Welcome to everybody. I'm Cristiano, physicist and lead AI scientist here at PySchool. So this is our, let's say, it's the first of our new talks called Spotlight. And this kind of talks are about PySchool of AI alumni success stories. So today, our host is Ivan. Ivan is a data scientist at IFAB, which is a non-profit organization in Bologna, Italy. He specializes in machine learning on HPC infrastructure and various aspects of large language models. He has a background in physics, mathematics, and in general complexity science. And in addition, Ivan is passionate about philosophy, and this led him to explore the vast depth of, all the technology landscape. This kind of talks, again, are for, we will invite alumni from the School of AI, and that's why Ivan is here. And Ivan was a fellow of the PySchool of AI session 13. And today, the title of the talk is a quick guide to essential tools for using training and accelerating inference in large language models. So again, thank you to everybody. Before leaving the floor to Ivan, I just want to remind you to follow PySchool social media accounts, for instance, LinkedIn, so you can be updated to about our projects, events, activities, talks, and especially I would like to highlight that we have just kicked off at PySchool our project with the European Space Agency, which is called LLM for EO, Large Language Model for Earth Observation, and we have a for it. I will put it in the chat in a while. And thank you again. And Ivan, it's your turn. So go ahead.
Yes, thank you, Cristiano, for the introduction. I really liked also the spotlight effect at the moment of introduction. Without further ado, let me go forward. You see my slide, I think, yes. I can proceed. I won't see you anymore, so if something goes wrong, please tell me. All right, so let's start with an agenda. We have quite a rich presentation. We start with an overview of LLMs, how we work very, very briefly, and then we start also seeing prompting tips regarding how to optimize the way we interact with these LLMs. Then we actually see quite in depth how to train LLMs, and then we touch briefly upon accelerating the inference of them. So if I need to present myself, actually, I think I would like to present my team. This is the team I've been working for the past year and a half at IFAB. I'm part of the project team. Great team of people. Like we have a quite diverse background, and it's quite good. But I'm here actually because I was part of the session 13 of PySchool of AI. You also see Rui today here in the presentation. Thank you, Rui, for joining. And I wanted to share with you a few things I did after the School of AI. So to start, I have to say that I came back with an enriched vision. So I had one more case study under the belt to bring to my team in order to improve the team overall. Then also I participated and achieved the first place in a prompting hackathon, I think in November or December last year, still of PySchool, organized with OpenAI. And I also partake in a training course for individuals who are interested in learning deep learning from the ground up in Sassari. This is also with Cristiano, who introduced me earlier. Also a very, very nice experience. All right, let's get into the technical stuff. We're gonna go first have a light passing view on, without getting too much into technical details, and then we're going to start to see more technical stuff. To start, let's have a zoom in on what is generative AI. So we talk about generative AI as a macro term, but actually there are different kinds of models. There are models that generate language. This is what we're going to actually talk about today. And these are the most famous: ChatGPT, Claude. Then we have models that generate images, and then we have also models that generate video. And I want to bring forward Dream Machine, which has been released not so long ago as free to play with, and also Suno and Udio are two other models that generate music, are quite fun. As I was saying, the focus is on the autoregressive types of model that are those that are used in order to generate language. And to have, let's say, a macroscopic view on how they function, the fundamental things we see right here in this box, where, let's say, we have the modular reasoning. Essentially, the model is autoregressive because it takes data and generates it one step at a time. The data it takes in are called the tokens. You can think about them as words. Basically, they are soft words. And once it is fed up all this input, it generates what we see in the table, namely a vocabulary distribution from which is going to draw the next token, and in such way repeat the process in an iterative step. We're going to see it in more detail, starting with the graph on the right. This is taken from Attention is All You Need, which is a paper published in 2017 by the Google team, which basically kickstarted all this focus we have nowadays with AI. What is interesting is that the GPTs actually care only about the right side part, which is called the decoder part of the transformer architecture, in order to generate the language. And the way it works, we can divide it in 3 steps. The first step, we have basically the input processing, where we take text, and then we transform it into numbers. The way we transform these text into numbers is called tokenization. And we start applying these weird and strange ways of transformation in order to then feed it to the transformer layer. And this process is called the part of embedding. And we also have a positional encoding part. We then continue with the, let's say, real manipulation of the data in order to gain an understanding what the model, what we can put in a bad analogy as the understanding of the model, where the key part is the multi-head self-attention, which was the main innovation of the 2017 paper. The big characteristic of the transformer, it allows not only to attend multiple tokens, but also to allow parallel training. And later we're going to see that this is a big and important characteristic for it. We then have a class standard methodology. We're not going to talk about it too much, in order to then reach the vocabulary distribution, so the table that we have seen before. Good. We have these models. How do we want to, how do we know which one we want to use in order to have the best, the latest and best model? But the way we can, the best I suggest to do it, I think it is widespread, is to check out this Chat Arena Leaderboard, just a website that you can go and look up, where we see, let's say, the ELO, so the score of the model, of each model. We see the first one still GPT-4o, and then the second one, this is actually a new entry, is Claude 3.5 Sonnet. So this is the medium kind of sized models that has been released this week. And what's interesting is actually that this model is at the moment the best at coding, apparently, and I think coding is one of the best implementation of LLMs. You can really do a lot of coding with it. I speak for experience because I'm a bad coder, but actually, man, thanks to them. Okay, I wanted to give also a focus on one thing. Usually, there are other models that are famous. Another model is Llama, for example, and we hear it as an open source kind of model. Llama 3 is the latest release. And it's not completely fair to call it an open source model because we see that essentially what they release is only the weights. So it will be more fair to just call it open weight. It's an open weight problem. If we want to check out a real open source problem, we can check out Olmo. Olmo is a project from the LLM AI Institute in Seattle, and they release not only the weights, but they release also the code, the data, weight and biases logs from the training runs. So useful stuff if you want to repeat experiments as scientists tend to do. So it is very interesting. Another interesting stuff is that it has been trained in Europe. So it has actually been trained on Lumi, which is the supercomputer from pre-exascale supercomputer from Finland. All right. This concludes like the overview. We're gonna pass now to a guide to prompting. To start, I leave this one. So this one also is a recent release. It has been brought about like a couple of days ago from the new implementation into the API from Claude. And we see also what is really useful for is this Claude prompting guide. I put a QR code here, very big. I hope you can scan it without problem, from which you can download it because I think it's just good material to have and check out. We don't have time in order to see it all here. Is 400 lines. But we can try to get some insights from it. So to start, so this is actually a file that Claude uses in order to improve our prompting, right? So we see already that how the file is formatted, we can gain insights in how we want to format our prompts itself. To start, we see quite an extensive use of punctuation and delimiters. We see the use of hashtags and the use of quotes and also words like such as prompt that help the model to understand which part of text is which helps then the reasoning. We see an example of two-shot prompting because we have a good and bad example of for each specific case, which then can be used by the model in order to, once it has fed with our example, use it in order to be improved. And we also see an example of chain of thought prompting. So let's see what is chain of thought prompting. Chain of thought prompting is usually abbreviated with COT. We see here on the right an example of chain of thought taken from the paper that discovered that using this method is actually improving the capability of the model by quite a lot. For example, here we have the same question represented left and right. On the left, we have an example with a shot. So an example provided when the question is asked, but the model is not able to answer correctly. Once this chain of thought that basically means explaining the reasoning that brought the answer to the previous question to be 11 in this case. So we see it here highlighted in blue. Once the chain of thought is applied, we have that the model can correctly answer to our question. This is a good example of why we want to use chain of prompting in when we interact with LLMs. On the left, we have another example of few-shot prompting. We just have many. In this case, we have 1, 2, 3, 4. Is a 4-shot, right? Yes, 4-shot kind of prompt. Where at the in the fifth case, we are asking the question and expecting the correct answer thanks to the information on the example provided before. This one is actually taken from a prompting guide that is freely available online. I will later share links. A link to it together with also other material that we are discussing today. All right, so we have these general techniques that can be used for prompting. What I want to pass by is actually this kind of split view that we should have or can have when we interact with ChatGPT, Claude, whatever LLM you're using, in order to improve the quality of responses we get. This basically is having both a vision of it as a tool, but also kind of trying to prompt a person. This is because we need to know that essentially GPT is a tool so that we can implement the use of the limiters, the use of examples. And this, a specific example that I highlighted is think step by step is what they meant by breaking down complex tasks and trying to implement this in order to then release this chain of thought by the model itself. So the model will try to output the steps in order to reach the solution. We need to have all this kind of insight on the model, but we also can kind of interact with it as we interact with a person. Not in order to engage in an emotional way with it, not at all. This is not what I'm proposing. I'm just saying that if we think that we're actually solving a problem together with a person, we tend to engage in a different kind of collaborative and team problem solving that we don't have if we think about it only as a tool. So having both this vision helps with the prompting. Yes. Let's pass now about training LLMs. The main message you want to pass by is this one, and then actually this one as well. So what is RAG? Featured prompting, we've seen it, and the fine-tuning. Why do I want to say this? So we're going to now try to unpack the two slides, so Schwarzenegger and Rambo. The RAG part, very quick. So I think RAG is one of the best solutions that we can implement. So usually if we are at a point where we want to discuss fine-tuning or RAG is because we have a task that we want to solve and a model that is not efficiently solving it, or it's costing too much for us. It's costing too much to us to solve it with such model, and we want to try to solve it with a smaller model. We can try to fine-tune or train an LLM for it. It's very difficult. If we can implement RAG, which is explained here quite simply in 3 steps, this is better. Let's see what is RAG. So first we have the standard part. We've seen it before. We try to prompt in the best way possible. This is maybe the biggest gain we can have is that we always implement full thought and chain of thought. We ask, then if this still is not sufficient, we can implement a component that before going asking the LLM our question actually goes and search and retrieve from a storage place. This is called sometimes a vector PD. There are peculiar ways. So cosine similarity is the method that is most often used in order to retrieve similar text to the one that we prompt the LLM with, so that we can retrieve it effectively. Essentially, what we need to know is that we grab some text from a database, from a repository, and we attach it together with our prompt in order to then give it to the LLM. Why? Because when the LLM is fed with this extra material, then its reply can be more accurate. Maybe it's also fed on something that it never saw before because proprietary material. We don't know. So there are many implementations for RAG, but essentially we have this 3-step process. You search retrieve some text to be fed together with the LLM, and then we give this to the LLM. All right, we were talking about training. So if you really have to train, we need to use distributed training. Distributed training is a huge word. We're going to talk what distributed training is. To start, I wanted to share with you this beautiful image. I think is very, very pretty. It's not generated by Midjourney or another kind of AI. This is actually a supercomputer that is in Barcelona. Is the Mare Nostrum, it's called, and it's a supercomputer hosted by the Supercomputing Center in Barcelona. And when we need to do distributed training, we are going to need something of this sort. We're going to need a cluster. Let's explain first why doing distributed training in the first place. So we have this thing that is called transformer that enabled us to train with a lot of data. We see that the more data we give it, the bigger the model is, the best our inference tends to be. This led to huge models. So we have GPT-3 is 175 billions, has 175 billions parameter within it. And in order to deal with such a beast, we need to have a monster computer as well. Together with that, we also have the fact that we usually give terabytes and terabytes of data to it. And having to deal with that on a single GPU is not easily impossible to think. We have an example. I think this is taken from an NVIDIA blog post that if you have to train a GPT-3 model with 175 billion parameters on 8 V100 GPUs, a type of GPU, it will take you 36 years. So already if you have 8 GPU is unfeasible to train. With 500 V100, it's going to take you 7 months to train. So we need to have many GPUs. We're talking about clusters, thousands of GPU probably used when training the large models by AI, OpenAI and Meta and Anthropic. So in order to do this, you need to have a bit of an understanding of the picture of Mare Nostrum. You can have is interested in trying to see this. So essentially what do we have? We have one shared storage where we put all the data. We have a nice speed network. This green line basically connects all these nodes together. So one little square here is a node. And all these nodes connected with a nice speed network enable us to do high-speed inference by means of many GPUs. So for each node, we tend to have usually 4, but it could be 2, 8. It depends on the cluster of reference. We have a number of GPUs attached to it. And what can we do? We can try to make use of this GPU. So we have usually we have single GPU, single node. So we have if we run inference on our laptop and we're lucky enough for computer, any workstation, personal workstation we have, and we're lucky enough to have a GPU. Most of the time, this is an NVIDIA GPU with the kernels in it, and we are able to install the kernels properly. Then our training of the machine learning model can be done on our GPU. And we are here in this first case of single GPU, single node, or the node will be our laptop or workstation. We then can scale up. We can do multi-GPU, single node. So it can happen that we want to train on multiple GPUs, but still we are restricted on a single node. This allows for faster training, obviously, but we are limited by the number of GPUs attached to our class, to our single node. If we want to go full on, like we can actually have multi-GPU, multi-node training. This allows the highest parallelism and scalability, and it is what is done in order to train the monster parameters, the monster models, sorry. All right. We have this multi-GPU, multi-node training. How do we do it? There are 4 different ways. First is the distributed data parallelism or data parallelism. And this is the one we're going to talk about more in detail. Essentially, just briefly, we split the data and we give it to multiple GPUs. Then we have fully sharded data parallelism, tensor parallelism, and pipeline parallelism. The level of complexity on this steps out quite fast. So the fully sharded data parallelism, we can think about it as a necessity that we encounter when we want to apply data parallelism, but our model is so big that it doesn't fit on a single GPU. something that can happen. We need to find another way. We go to this fully shuffled data pattern. Tensor parallelism is another model that is another framework that we can use in order to split parts of the model into different GPUs and then allow training even between different GPUs for different parts of the model at different times. But we still run a single run. And there is pipeline parallelism that we have, let's say, a combination of these. We're not going to talk about that. Let's focus on the data parallelism. We're going to see it in depth. To see it in depth, let's bring to our cache. So we get into the bandwidth memory. We recall how a single GPU training usually works. We can consider it a three-step process. We have the first part where the model receives an input batch from our data loader. So we have data here somewhere. We give it to the data loader. The input batch gets the data loader outputs the input batch. This input batch is given to the model. The model, what does it do? It computes a forward and a backward pass. Once it has finished to compute the backward pass, the model has actually accumulated some gradients, and these gradients can then be used by the optimizer in order to update the model weights. We do this many times. We have our model that is able to recognize digits, for example. What happens with a multi-GPU training in this case in the data parallelism? So the first step is that this DDP is the specific also is how it's called in PyTorch. The DDP takes the model and makes 4 copies of it, one for each. In this case, 4 because we have, let's say, n identical copies. Let's say that n is 4, so we have 4 copies of the model, one for each GPU. We're training it on 4 GPUs. Once these copies are made, we actually introduce an extra component we did not have before that is called the distributed sampler. We have this distributed sample doing the task of splitting the data. We split the data in 4 pieces. In this case, we pass it one piece for each process. So one part of the data set for each of the 4 GPUs. We then have parallel processing going on, and therefore we have the main data parallelism. But the main focus is actually on the splitting of the parallelism. We have a complication from this. What happens is that if we give the data to the different models, we're going to go forward with the model with the process we have seen before, that is compute the forward path, compute the backward path, get the gradients. What happens is that the gradients are different. We then have different columns of gradients for each GPU. If you're then going to try to update the model now, the model weights now, each model is going to be different, and we're not effectively training in parallel. We then have to have a synchronization step. This synchronization step is made automatically by this DDP attribute in PyTorch. It's done through a node-reduce method, and what happens is that this synchronization allows to aggregate the gradients. So we don't have 4 different colors anymore, but we have the models colored with 4 colors each time. This is very cool. It happens. The synchronization step happens straight as we start the calculation of the backward pass, so we don't have idle time of GPUs, and this also allows for improved performance in training. Once we have all our models, we finish all our gradients. So for the models, we finish the backward pass. Those are all synchronized. We can update the weights as we do in a regular training run, and this time each model is going to be updated accordingly, and we can do another pass, then have the final model. Okay. Let's talk about why torch distributed is a good method for it. So to start off, it integrates very smoothly with Workload Manager. Most often not, Workload Manager is Slurm. So you can run your training code with Slurm quite easily. And then it's also not too hard to go from a simple from a single node to a multi-node training. This is also true when we have multi-GPU, and this is a big help. And also the fact is that we're using native PyTorch, so we don't have extra frameworks. In case though an extra framework is required, because for different use cases, we might have one code that already uses another framework, whatever reason, I don't know. There are situations where we want to use other frameworks, and the two most popular ones for distributed training are Orvod and Retrain, and this is also something you can start looking into if you're interested into the distributed training. All right, we talked about distributed training. We want to see very briefly about the fine-tuning part, right? So we discussed the fact that RAG is usually a good way to improve our model, but maybe the outcome of our model, we've improved 80%, we want to improve another 10%. What we can do is to do some fine-tuning. So this is, in my experience, is something that is the most confused. Like, people confuse always exchange RAG and fine-tuning, because if you lay on a third-party app, most of the time you're actually getting back a RAG implementation, not a fine-tuning implementation. It's a very nice engineering challenge, though, and if we want to have a bit more insight into these engineering channels, two methods that we should know are the LoRa and the QLoRa methods in order to implement fine-tuning. Why these models? What do we do? So to start, what will be traditional fine-tuning? Ideally, so you have the model, it has been trained, you have some extra data, you want to train it again. You can do this. In case you have a model that is, it has 175 billion parameter or more, the fine-tuning is the traditional fine-tuning has a high memory requirement, it is computationally expensive, and you also have the risk of catastrophic forgetting, which is the event where you improve slightly the benchmark on your specific task, so the data you pass for fine-tuning, but you lose points on all other tasks on the benchmark. So you kind of have an improvement on one side, but overall a decrease in performance, which is not ideal. In order to minimize this risk, you cannot really avoid it, but you can minimize it with the LoRa, low rank adaptation method. This is very cool. It also has a really interesting, it has a very interesting reason for working. This lays, I think, from a paper written by Uber that showed that essentially, even though we have a very large vector space where our solution moves, that the dimension is essentially the number of parameters that the model has. So when we train mathematically, we can kind of bring down the process of training a neural net into finding a steady-state vector within this space, and for the case of GPT-3 is 175 billion. It has 175 billion dimensions. Even though this is the case, when we find how the model moves through this and what the solution actually requires, we find out that the final solution can be condensed in very much smaller number of dimensions, and this also in turn implies that we can focus on these dimensions that are important for the model training, for the model solution, to then improve the final performance. And this is somewhat corresponds to in LoRa the fact that we only take, now I complicated a bit with the theoretical part. Essentially, we take the final layers, we try to freeze most of the other layers, so we update only the weights in the final layer, and we see that overall is the performance is improving. We can also do additionally this quantized LoRa. So we can apply this low rank matrices method, a further optimization with quantization that reduces memory usage even further. This allows to then fine-tune even large models, maybe Llama 7B on a couple of GPUs, and you maintain, more or less, you maintain the same quality of very limited loss in performance. So those are two methods that are really important to know if you want to learn about fine-tuning. Even better, like if you decide to get into it, you can check out this paper. It's called RAG versus fine-tuning. It's from Microsoft, and goes in depth into a bit comparing on a specific case study, the difference between a RAG and fine-tuning, and we see that, spoiler alert, the solution are more or less the same. So it doesn't matter too much if you RAG or if fine-tune. The most important thing is the information content in your data to then improve the result. If you combine the two, you have a better performance. All right, sharp turn, very sharp turn, we change subject. We go into speaking about accelerating inference. What about accelerating inference? So in the first place, what is it? What actually are we doing? We see it in this image. Ideally, we want to have solutions that are more on the right, so more like this than like this, right? So essentially, inference is the speed at which we are spitting out the tokens. And there are ways in which we can try to move from 25 tokens per second to 246 tokens per second. What I will show in the next slides is actually taken from a blog post from this guy. It's called Horace E. Very good. I really like him. I would suggest one to read his blog post, Making Deep Learning Go brr, brr, from first principles. And the second one is the one that actually accelerating generative AI with PyTorch. GPT-Fast is the one that we're going to see in the next slide. So to start off, what is the bottleneck? Why sometimes we have 25 tokens per second, but we can bring it to more than 100 tokens, 200 tokens per second? The largest bottleneck usually tends to be how the CPU and the GPU interact. So we have seen how distributed prompting. Let me check one second.
No. It was a mistake on my end. Ignore.
Sorry. Okay. So we have the situation where we're zooming in now. So let's not get confused with the distributed network, right? We have seen what is a node, what is a multi-node. Now we're thinking only just how also in our laptop, if we have a laptop with the GPU, how the CPU and the GPU interact. Most of the time, what happens is that we are providing the GPU with an instruction, but with the CPU. So the CPU little card here brings an instruction, in this case, add to the GPU. The problem is that the GPU is this huge, large factory that then computes a lot of things very fast. And the CPU needs to go back and forward from the cache, from the memory to the GPU to bring these instructions. If we do this, we are limited, because then what happens is that there is not much fuel coming on, because we burn a little operation, then the GPU shuts down, And then we need to wait for the car to go home and come back and give another operation. In order to improve this, what we can do is to simply give more operations to the GPU all at once. The way we do this is by giving this graph, a graph with a lot of operation that the CPU can bring to the GPU in one single go. And this way, the GPU will take all the graph, break them down, and reduce the idle time. When it will be done, it will provide the CPU cap some information. The CPU will do another round, but instead of going back and forward hundreds of thousands of times, it can do it in just hundreds of times, and we finish our batch. And this is something that is very good for performance. The very cool thing, and here there are a few caveats. I will not go into depth on how actually this works, but I still send you back to the RSC blog post if you want to know more. In any case, the nice thing is that this job of having the graph, the huge graph, rather than the single add operation, can be done basically one line of code in PyTorch, which is this torch compile. Also, we need to specify this reduce overhead, that's important. But in any case, it's very interesting that we have a single instruction that can save up a lot of time. And this is an implementation of a fast solution. So we already, I'm not bringing the specific case that Horace explains in his blog post, which shows like already an increase of 70% or something like that, but it's quite good of an improvement. We have another bottleneck that is very common, which is this fact that so we have input, we have the model with these heavy weights, so large weights coming into it. What does it mean to have large weights? Essentially, we have one metric that's called MBU. This is model bandwidth utilization. It is given by this formula of number of parameters times the bytes per parameter. So this is how much the parameter weighs in memory, times token per second over the memory bandwidth of our particular GPU. And he does this computation where he has if he trains with an A100 Llama 70B, by default, the parameters are stored into FP16, floating point 16, which means 16 bits, 2 bytes. So we have that 2 in these 2. And then he has this number of tokens per second that already was improved from 25 to 170. If you divide by the memory bandwidth of the A100, that has a theoretical limit of 2 terabytes per second, then we're already at 72% of the theoretical of this theoretical limit, which means that you cannot really improve that much. Like he says that already simple operations such as copying memory, you get already 95% of memory bandwidth utilization. So you have little room in order to improve. What can we do in order to solve this issue? We can quantize. What do we do essentially is we have these bytes per parameter here. We can simply half it by switching from an FP16 to an int8. And essentially the quantization part is what we see here, where we have a floating point number that is stored with 8 digits. We can then store it in 4 digits with the 8-bit integer. That's simply the operation. In this way, we are decreasing a bit the model performance, right? Because essentially we are giving less information. The fact is that this is the information stored in a single parameter. If you think about it, it's not very important to have, let's use again the analogy with bodybuilders. You can avoid having a Schwarzenegger as a single parameter, but have many Rambos, so that overall you have a better effect. What appears to be, so what emerges be the intelligence of the model stems more from the parameter interaction rather than the parameter size. And so we have a small decrease in performance, but we have an improvement into inference, which is something desirable most of the case. All right, we can pass by into, let's say, an experiment setting very briefly. We talked a lot about performance in this case. We've seen both in training and inference, very distinct areas, but in both cases, you need to get a bit technical in order to understand what's going on. I find that basically one of the best tools that we can use in order to cope these problems is the PyTorch profiler. What is the PyTorch profiler? Essentially, this activity tracking. You can track the performance analysis tool. You can track the performance on the CPU and the GPU, the memory consumption. You have the visualization of the timeline, so you more or less understand where in the process you are having your bottlenecks. And it has very good profiling capabilities also for CUDA kernel. And so essentially, why the PyTorch profiler? If we're actually testing for better speed, we usually have two methods, right? Better speed or performance. We have two methods. The first part is that simply the model didn't work and started working. And okay, it's good. Maybe we couldn't fit it. We couldn't fit the model into our GPU. We applied quantization. Now we can run it. We're happy. Fair enough. This is the first test. If we need to actually check how to go from there to an even better model, then we need to have a tool in order to have the magnifying glass on where to go. And this is what the PyTorch profiler provides. What is very cool also is that it can be linked to TensorBoard. This opens an interesting side note. The side note is that the Google team itself helped bridging the gap between TensorBoard and PyTorch profiler. PyTorch is developed by Meta, was developed originally by Meta, which proves itself, proves that PyTorch is a very, very capable instrument. So maybe even researchers within Google tends to favor PyTorch over TensorBoard. If we then help to build a bridge between TensorBoard and PyTorch profile, they can also just push their TensorBoard product, but I think they do use PyTorch profiler. It's a bit of a mess to make it work, but it's not too hard. You need to add the proper dependencies in order to have TensorBoard working with PyTorch. Once you actually have it running, you can do very interesting stuff. So you have all this information color coded. It even gives you performance recommendations straight in the back. So here, if you cannot read here, one interesting thing it says is you could enable automatic mix precision to speed up by using FP16. So it already suggests or recommends some kind of tactics that you can implement in order to have better performance, and we recommend to check it out if you get interested into that. All right, this brings us to the end. Let me do a recap of what we have seen. So the first part, I think, is the most important. We have to be careful about prompting. Essentially, the highest performance gains are always users, people that use it or do not use it. I said, is how you interact with it. If you're aware of the prompting guide suggestions, so if you can implement a chain of thought, few-shot prompting, use the delimiters appropriately, then the quality of the answer you're going to get is going to increase a lot. This is very useful. If you then need to have another performance boost for whatever reason, I would suggest to prefer, try to prefer RAG over fine-tuning. And so have it as the first go for your prototype solutions. if you have still need to have some improvement because the RAG itself is not sufficient, then you can it's proper to try to do some fine tune. In order to do the fine tuning, you need to be aware a bit of the infrastructure you're using. Even if you use a cloud provider, also be aware of this interaction of data parallelism. Have clear in mind the relation between multi-node, multi-GPU or multi-GPU on a single node in order to then implement the correct solution. If you can, try to work on a single GPU. For most cases, I think there are models that are not that big that will suit the need of fitting into maybe a 100 GPU. And then exploit the data parallelism because it's not too difficult to implement and you get quite good results of optimization with data parallelism itself. Then also, if you cannot do that, try then you need to switch. You have to go to tensor parallelism, maybe pipeline parallelism. Finally, beware of quick implementation in native PyTorch that you can use in order to speed up the inference. We saw Torch compile, we saw quantization. And finally, if you need to test the PyTorch profiler and TensorBoard are probably your best friends. All right. I will conclude here. If there are any questions,
Thank you, Ivan. Interesting and update. So yes, if there are any questions.
I cannot hear you, Cristiano.
Yeah, I think something's wrong with this connection.
Are there any other questions for Ivan?
I have one.
I have a question, Ivan. So, yeah. Okay, go, Marcelo.
It's about a previous topic when you talked about parallel training, having multiple GPUs. And you say that the issues were synchronizing then the gradient computed by each GPU. So if this is synchronous, it means that there is a bottleneck in terms that the entire collection of GPUs go as fast as the slowest GPU. All the GPU have to wait the slowest one. Is that correct?
Yes.
Okay.
Yes.
So that's a pity.
Yeah. Like in the end, the best I can do, right, is to have the synchronization happens simultaneously to the backup pass. So you don't wait until the GPUs are done and then you give the update of the gradients throughout all the different models stored in the different GPUs. But you are still bounded by the fact that all GPUs need to end before you can go on and use the optimizer to update the model. So in the end, if there are differences between the different GPUs, then you need to wait for the lower GPU. So usually they tend to be the same kind of GPUs. So then you can have similar results. So not much lag between one GPU and the other.
So it doesn't make sense to have a lot of really shitty GPUs and one awesome one, because you have to wait for the others.
There it becomes interesting. I think so. It's if you have more computing power, is always better, right? Then it becomes a matter of how you can exploit it effectively.
Yeah, that's true.
So maybe there, it could be interesting to have different. If you want to go more deep into it, into this separate, do some tensor parallelism, so that maybe you give one part where it's very important that you have a powerful GPU. So usually this is the case for the attention heads that needs high bandwidth in order to get a lot of weight. So all of a sudden, and you give this part of the model to the strong GPU, and then maybe parts of the fully connected layers in the transformer you give to the shitty GPU. This might be also an approach, but there it becomes a bit more complicated.
Okay, thank you.
I have a
So
question
visual-
for Ivan. Yeah. Okay. First of all, great talk. But the second part of it was particularly interesting. My question is, I mean, there's an explosion of tools and libraries that we have now, and of all of them, Hugging Face seems to be the most popular choice for, say, fine-tuning LLMs. But it was really refreshing to see the entire PyTorch ecosystem laid out. So in terms of your personal choice, what is your favorite library to use when on LLM applications?
Yeah, PyTorch, definitely. Like this talk also has the motivation behind convincing one of my colleagues that is full on TensorFlow to come to the PyTorch. So usually I thought that I thought that PyTorch was.
Are there still persons with TensorFlow? They
Yes,
still
yes.
exist?
Yes, I mean it's still good, right? Also, like I found out, for example, the other day I was checking an example for LMC's competition, a Kaggle competition for the chatbot arena and stuff, and there was the Keras that posted a notebook, and the notebook in Keras that was using the beta was performing better with JAX, than with PyTorch. So maybe it's still like it's not an overall win. There might be cases where still one of the three methods. I mean, the three methods are these now, right? TensorFlow, PyTorch, or JAX. I think there is particular use cases where one is to be preferred with respect to PyTorch, but I think overall PyTorch is the best.
Does PyTorch have, I mean, as far as I know, the most unique, the best thing about TensorFlow was that it had a very thriving ecosystem for embedded models. Like if you want to serve a model to mobile or like an embedded device, it was really easy to do that with TensorFlow than with PyTorch. But I know that there was something called ExecuTorch. Do you have any idea about it?
Which one is the last one you said?
It's called ExecuTorch. Yeah, I mean that seemed to be the new thing for PyTorch mobile, but I don't know. That's why.
No, actually, that
do you
one
have
I
any
never.
idea about this?
No, I haven't. In fact, thank you for mentioning. I didn't check it out. Also, the other one that I want to dig a bit deeper into is PyTorch Lightning, which is also something I don't use, but I think it's very powerful. So it's a cute up. Seems cool.
Yeah, they have their own library called GPT, which also seems to be an interesting competitor.
Yeah, it's very interesting. For everyone, I put a lot of sources that I used for the talk in the chat. So if you want to have a look at the sources, I think we're good.
And this is awesome. Thank you.
Thank you. So, if there are no further questions, I would thank again Ivan and everybody else that joined us. And soon there will be another spotlight talk in the next week. So again, follow our social media and follow also Ivan on LinkedIn. And what else? That's all from my side. Thank you again, and have a good evening.